Hey class, Math 1513 College Algebra. We're at Northern Oklahoma College. I'm doing a combined lesson on 3.2 to 3.4. We are still finding all the zeros, all the x-intercepts, all the roots of a polynomial. So let's call this part 3. Because part 2 was, I kind of got interrupted and cut off. So part 3, we keep on going. All right, look at this polynomial. X to the fifth minus 25x cubed plus 144x. What do we know without even doing anything yet? What do we know just by looking at the polynomial? I know it has probably 5 roots. Some of those roots might be complex. Some of them real, some of them complex. What about the shape of the graph? And x to the fifth graph is going to go down to the left and up to the right. So it's going to go up, down, and back up. It's going to look something like that. Now, depending on where the x-axis is, if the x-axis is up here, we might have just one real zero. If the x-axis is down here, well, heck, we could have 1, 2, 3, 4, 5 real zeros. So let's find out what happens. First thing I notice is that each of those terms has an x in it. So let's factor that x out. So we pull that x out front, and now we have x times x to the fourth minus 25x squared plus 144. Okay, at this point, I'm going to take a peek at the graph. And I notice when I peek at my graphing calculator that I might have zeros at 3, 4, and -4. So I'm just going to start testing those zeros. Now, I'm going to start with -4. You can start with any zero, any root, any x-intercept. I'm just going to pick -4 at random, and I'm going to use synthetic division on this part of the polynomial here and see if -4 really is a root, a zero. So I have 1 for my x to the fourth coefficient. I don't have an x cubed coefficient, so that's a 0. My x squared coefficient is -25, and my x coefficient, which I don't have an x, is 0, and my constant is 144. I'm testing -4. I want to see if that's an x-intercept. I want to see if that's a root, if it's a 0. So let's test -4 and see how it works out. And that's what I got. I got a 0 remainder. That means -4 is a root. It also means that x plus 4 is a factor. All right, because remember, it's x minus the root, or x minus the 0. So x minus the -4 root is really x plus 4. So x plus 4 is a 0. Sorry, not a 0. X plus 4 is a factor. -4 is the 0. So what does my polynomial look like now? I still have my x out front. I just found out that x plus 4 is a factor. And what's left over? Well, that's going to be my numbers right here. Okay? 36 is my constant. This is my x. This is my x squared. This is my x cubed. And so I move all of that right there. And now I have p of x. My polynomial p is x times x plus 4, the factor we just found, times the rest of it, x cubed, 4x squared, 9x, 36. All right, now let's look at this remaining polynomial here, and let's test one of the other roots. Now, I suspected that 3 was probably a 0 from peeking at the graphing calculator. So let's test the number 3. Let's see if 3 is a root or a 0. So I have my coefficients, 1, -4, -9, and 36. From these coefficients right here, and I'm going to check the root 3, or the 0, 3. I want to see if that's one of my x-intercepts. Why don't you guys pause the video and do that synthetic division real quick. And I got a remainder of 0 again. That means, yes, that means 3 is a 0. It also means that x minus my 0, minus my root, which is 3, it means x minus my 0 is a factor. So what do we have now? We have our x. We have our x plus 4 that we found in the last synthetic division. What did we just find? We found that x minus 3 is also a factor. And what's left over? Well, that's just right here. That's going to be my -12 is my constant, -1 is my x, and 1 is my x squared. Okay, I still need to look at this polynomial right here and see if it'll factor further. Now, if you're pretty sharp, you'll see that this splits. We could factor this just using the regular factoring method into x minus 4, x plus 3. So that's one way of factoring that final polynomial. So my final answer would be that right there. So p of x, my polynomial p, would be that right there. But if you're not able to spot that, well, then we just go back to our synthetic division. We're looking at this polynomial. I got my 1, my -1, and my -12 ready to go for synthetic division. I've peeked at the graph, and I think that 4 may be another 0, so I'm going to test it with synthetic division. I find out my remainder is 0, so that means 4 is a 0. And x minus 4 is a factor. So what does our polynomial p look like now? We have our x times our x plus 4 that we found in the first division, times our x minus 3, which we found in the second division, times our x minus 4 that we found in our third division, times whatever is left over, and that's over here. 3 is my constant, and 1 is my x. So x plus 3. So that is my polynomial written as a product of its factors. All I have left to do is list my zeros. Okay, well this x right here, that's going to be a 0. X plus 4 means that -4 is a 0. X minus 3 means that 3 is a 0. X minus 4 means that 4 is a 0. And x plus 3 means that -3 is a 0. So there's my 5 real zeros. Remember at the beginning we said there might be 5 real zeros. We might just have 3 real zeros and 2 imaginary zeros. You just never know where that x-intercept is going to cross. But in this case it crossed all 5 of those curves. So our graph is going to look something like this. It's going to go down to the left and up to the right. And all of those zeros it's going to cross, because all of those zeros had an exponent of 1. Whoops, I'm down here. Exponent of 1, exponent of 1, exponent of 1, exponent of 1, exponent of 1. That means the line's going to cross at every one of those zeros. So let's just start crossing. Cross, turn around, cross, turn around, cross, turn around, cross, turn around, and cross again. So it crosses 5 times. Now remember, this isn't an exact graph, but it's a pretty good sketch, okay? Okay, let's talk for a minute about complex zeros, or imaginary zeros. Imaginary is just what you think it means. Imaginary things don't really exist. So complex or imaginary zeros, they don't really cross the x-axis. Think about it like this. If I have an x cubed graph that maybe crosses here, and crosses here, and crosses here, well, we have 3 very real zeros that we can see and touch. But what if that x-axis had instead gone across right here? What if that had been our x-axis right here? If that had been our x-axis instead, we would only have 1 real zero, and we'd have what we call imaginary zeros right here where the little hump should have crossed normally. So we call those imaginary or complex zeros. They should have crossed. That should have dipped down and crossed the x-axis, but it didn't quite make it. If it had gone a little bit further and dipped down, then we would have 2 more real zeros. But that hump didn't come down quite far enough, so we have what we call complex zeros or imaginary zeros. So if you see an x cubed graph, you know an x cubed graph kind of looks like this. If you see an x cubed graph that crosses the x only in one spot, well, you know that 3 on the exponent says we should have 3 zeros. Well, here's our 1 real zero. What happened to the other 2? Well, they're right in here, basically. Just think of it like that. You have 2 imaginary or complex zeros that didn't quite cross the x-axis. You have 1 real zero and 2 complex zeros. But in a nice, easy world, an x cubed graph would have 3 real zeros. Sad fact is, it doesn't always work that way. Sometimes we have some complex zeros that we have to deal with. All right, take a look at this one. What do I know so far? I know it probably has 3 zeros. Now, it might be 1 real zero, it might be 3 real zeros. We might have a couple imaginary zeros to deal with. I also know it's an x cubed graph, so I know it's going to look something like that. Now I get my graphing calculator out, and I look at it, I take a peek at the graph, and it looks like I might have a zero at negative 1/2. So let's check it and see if it gives us a remainder of 0. I got my 2 from my x cubed, my negative 7 from the squared, my 22 from the x, and my 13 constant. I'm dividing by the root, negative 0.5 or negative 1/2, same thing. I'm going to see if it works out. All right, and I get a 0 remainder right here, which means it goes in evenly, which means it is divisible by negative 0.5, which means that negative 0.5 or negative 1/2, you can use either number, is a 0. It also means that x plus 0.5, because x minus the 0 would be x minus negative 1/2, or x plus 0.5. That means that x plus 0.5 is a factor. So what's our polynomial look like now? It looks like x plus 1/2, that's the factor we just found, times whatever's left over. What's left over? Well, it looks like 26 is my constant, negative 8 is my x, and 2 is my x squared. All right, I got good news and I got bad news. The bad news is it won't factor. The good news is we get to use the quadratic formula. Or maybe that's bad news too. Yeah, I know, the quadratic formula is no fun. But I peeked at my graph and I can't see any more real roots. So what we're looking for is imaginary or complex roots. So the only way to factor this right here, the only way to factor it any further that I can think of is just to go to our last resort, our quadratic formula, because you can always use the quadratic formula, it just takes a lot of work. Now remember, on the quadratic, this is going to be my A, this is going to be my B, and that's going to be my C. Remember, your B is negative 8. Let's plug it in and work it out. Here's the substitution. Remember to use parentheses when you're plugging numbers in for A, B, and C. That keeps your negatives straight. And we work it all the way out, and we find that x could be 2 plus 3i or 2 minus 3i. Those are our 2 remaining complex roots. So let's replace this polynomial right here with our 2 complex roots. So we have x minus 2 plus 3i and x minus 2 minus 3i, which we're going to clean up to x minus 2 minus 3i, x minus 2 plus 3i when you distribute that negative out. So there's our factors. What are our zeros? Negative 1/2, 2 plus 3i, and 2 minus 3i. And there's a peek at the graph with a real root and a couple of complex roots. All right, last one for this lesson. We have this polynomial. Looks like it has 4 zeros. Some of them might be complex, we'll see. And an x to the 4th graph is going to look kind of like a W shape. So that's kind of where we're headed. I'm going to grab my graphing calculator and take a peek at the graph. I see that there's a possible real 0 at 2, but I also see on the graph that it bounces. You guys remember when something comes down and bounces, it just touches it in one place? So even though it looks like it touches it in one place, there's actually 2 zeros there. So we call that multiplicity 2. That 0 is happening twice. That means that x minus 2 is going to occur twice as a factor. Okay, x minus 2 will happen twice. So I check my 0, my root, my x-intercept of 2. So I check it here. It goes in with a 0 remainder. So I know that 2 is a root, and I know that x minus 2 is a factor. I also know that since it bounced on the graph, it's going to occur twice. So what do we have now? Well, since I know that it's going to happen twice, that means that I can run it through the synthetic division twice. So let's check it again. And there we have it. It went through the division twice. That means it occurs as a factor twice. So here it is occurring twice with our leftovers of x squared minus 4. There's no x term because we got a 0 there. Oh, my fault. That was x squared plus 4. That doesn't factor. We got to go back to the quadratic formula. And my 15 minutes are up, but there's the rest of the problem.